All right, guys, good morning. Might as well get started now. Can you guys hear me okay at the back of the room? Yeah? Louder? All right, I'll try. All right, guys, so this talk is about building a sort of a reference architecture for connected devices. I'm Suji Maniyam. I'm a founder of a company called Elephant Scale. Basically, our forte is big data. We do a lot of consulting and training around it. And we also wrote a couple of books. One of them is called HADOOP Illuminated. That is actually open source. So if you search for HADOOP Illuminated, you'll get it. Okay, so that's all the marketing there is in this talk. All right, so Internet of Things, right? So, you know, when you say this thing, you know, Internet of Things, connected devices, most people roll their eyes and say, oh my God, you know, like, yeah, it's such a buzzword. Is it even real, right? But you know what? It is. So, you know, I have a little Fitbit. The other day I was walking around, and I already, so I made my daily goal. So my device syncs with my phone, and within like few seconds, I got an email from Fitbit saying, oh, you know, congrats, you know, you earned this badge, right? So to me, that was like, oh, cool. You know, like within like a few seconds, my device talked to my phone uploaded the data to, Fitbit servers, and then, you know, they actually send me like a little, email. So yeah, so these are very much in reality. So now let's say, you know, you are sort of designing the next Fitbit, or, you know, any connected devices. So you have a little device, and, you know, you have all these cool analytics. So what's in between, right? I mean, what's sort of the infrastructure or the architecture that's going to power all this? That's what this talk is all about, right? If you want to go and build something on your own, what does it take? So I only have about 20-30 minutes, I think, so I'm going to sort of zip through it. But I'm happy to, you know, take your questions afterwards, right? All right, so let's see, you know, let's talk about how much data we are talking about, right? So imagine I have 1 million sensors. Each sensor reports every minute, which is, you know, not very unusual. And the data packet size is 1K. So basically, you know, at the end of the day, you will get about, you know, 1+ billion events a day. When I ran these numbers, I ran in my, like a little calculator. I thought I was really getting some sort of a round error, right? Then I sort of go to Excel and then sort of try it out and say, you know what, yeah, this is really correct. Yeah, so you are going to get 1+ billion events a day, and your data size is going to be, you're going to get 1+ terabytes a day, right? Just a modest use of sensors. And, you know, this is the Excel spreadsheet to prove it, right? I mean, you know, I'm not making this up. And here is a similar data set from Texas utilities. So they have smart meters which send, I think they report every 15 minutes. The data size is about 4K. And yeah, so they cannot get the same numbers, right? I mean, basically they are very close to 1 billion events per day, about, you know, plus, you know, 1.5 terabytes a day. Now this, you know, right, by any definition is big data, isn't it? Right? I mean, because, you know, I mean, these are sizes we don't usually deal with, right? Not only we have big data, our sensors are sending events, constantly, and your data keeps coming at you at very high speed. So, like, you know, the same metrics. If you say there's 1 million sensors each minute, you're going to be processing about 17,000 events a second, right? So that's a pretty high volume. And so, you know, this is what we call sort of fire hose, right? Your data never stops. It just keeps coming at you, and, you know, it never ceases. And also, there are times when you sort of do this, there are times there are going to be spikes. For example, let's say, you know, you're processing some sort of a temperature sensor. Most of the time, your data is pretty normal. Yeah, it's between like 68 degrees and 72 degrees. Yeah, right? I mean, that's kind of what we want. But suddenly the temperature spikes, and then that's an interesting event, right? We had to process it. Maybe there's a fire. We need to send out an alert, right? So the challenge in event processing in big data in real time is most of the events are mundane. Right? I mean, you know, they're just regular within your normal parameters. However, any of the events could be important. So if you're doing this, I can't lose any event, right? Because any event could be important. And I need to process them in sort of near real time, because, you know, I can't wait like 3 hours to, you know, send an alert if there's a fire breakout, right? And I need to be able to kind of store them for audit and diagnose and all the stuff, right? And I want to be able to do some cool analytics. I want to say, what's the temperature in, you know, this zip code, right? So for this, if you're sort of dividing this architecture at a very high level, I sort of broken up into, like, you know, sort of 4 components: capture, process, store, and query, right? And right now these are all like black clouds because, you know, we don't know what's in them yet. So what we are going to look at is we're going to look at each of these components and see what we will do to build this out. So let's look at capture, right? So capture, we saw the requirements already, like, process thousands of events in near real time or near real time. Don't lose any events, right? Because any event could be important, but most events are mundane, right? So that's kind of the challenge. And also, I want to make sure, I can sort of survive hardware, software failure, and put a scale easily at the bottom. Easily is in code because, that's kind of a relative term, right? So what are our choices? A few choices if we are looking at this is like, you can use MQ, which is, very popular in enterprise worlds. Fluentd, Flume is sort of more like a Hadoop, part of the Hadoop ecosystem. Kinesis is a message queue on Amazon. So it's pretty much like a sort of hands-free message system. You set it up, and then it scales automatically, and captures events, so on and so forth. What I really want to look at is something called KAFKA. Right? KAFKA is a distributed queue. KAFKA came out of LinkedIn. It was kind of obscure at the start, but now it's very popular, right? Along with Kafka and Spark, Kafka has kind of become a little bit of a star. So you can see in LinkedIn they use Kafka very seriously, right? You can see like billions of images per day. So you can see it can handle events at a very high capacity. Very quick look at the architecture. So again, sort of the Kafka works in the sort of the pub sub or the producer consumer model. Producers push events to a Kafka cluster, and consumers pull it out on the other end, right? At a very simple, very high level. But all of this, if you sort of zoom into the cluster, these are all running on multiple nodes. So it's failure. The redundancy is built in. Your events are replicated. So even if one node fails, your data is available on other nodes. So the whole system is built to withstand system crashes, right? And another cool thing is you can sort of classify your queue into like different queues. So I can say, I can create a queue for like sensor data. I can create another queue, say alerts, emails, and maybe I can assign priorities and say, if it's alerts, process alerts, as quickly as possible. Emails, it's okay. We can sort of, we can process them a little later, right? So Kafka gives us all of those cool features, and you can see, all the Kafka use cases. So it's pretty well established. So for capture, I think Kafka could be a very good choice, right? Because it's built for fault tolerance, built to handle a really large amount of data, and it scales pretty easily. All right. So now this part we sort of said, yeah, we are going to use Kafka. Let's take a look at process. So remember, Kafka is just a queue. We need to basically start processing events real time or near real time, and the events are coming at very high velocity. We saw the numbers already. When processing, we need some sort of a guarantee that we will at least process an event at a time. Meaning no events are dropped from the queue. So these are what you call at least once, exactly once. So at least once is easy enough to do. Meaning like an event gets dropped, it may be picked up and processed by another node. That's okay. Exactly once, meaning you only guarantee you process an event exactly one time. That's a little hard to achieve. But for most of our cases, at least once is good enough, right? Because that basically guarantees, I will go through all the events. No events are dropped. So again, the choice here is, we have a few. Storm was the original stream processing, came out of Twitter. Samza, and then there's a new thing called NiFi, which is also very much data flow oriented. What I'm going to look at is Spark streaming. Right, so Spark is sort of the I'm sure most of you have heard of Spark, sort of the cool kid, right? The reason people are really gaga about Spark is the unified framework, meaning it has all of these things built into one nice platform. And so my kind of take on Spark versus Hadoop is like, I'm sure you guys have seen this ad, right? I'm a PC, I'm a Mac, right? So this is my take on the whole thing, right? This is Hadoop, yeah, it's a workhorse, yeah, we all know it. Yeah, it's not, it's kind of, but Spark is the cool kid on the block. So very quickly, Spark, as you can see, is built basic core, but it gives you lots of components. So for example, Spark SQL, meaning it allows you to do SQL queries on data, streaming, real-time, machine learning, and graph processing, right? What we are going to concentrate is on machine learning. And another thing Spark does very nicely is, since Spark is a compute engine, Spark doesn't give you storage. So Spark gives you an abstraction called RDDs. What they do is they abstract. You can read data from any of these sources. So Spark is basically a storage agnostic, right? So you can read data from HDFS. You can read data from Cassandra. You can do a join and then push the results back to some other storage. So Spark is pretty data agnostic, which is pretty great. So the reason we are choosing Spark is not only it gives us streaming, but also it gives us and a lot of analytics capability. There's machine learning built in. So it's like a unified stack. So basically, that's probably the only stack I really need. And looking at Spark streaming, so that you can see, my data comes through all of these sources, and then I go through my streaming engine, and I'm going to push them, save them to like a database or HDFS, what have you. Streaming is again very popular, very established, so a lot of people use it. So that's our choice for processing, meaning this is going to basically, Spark is actually going to process events out of Kafka in real time or near real time. So next component, storage, right? So storage, so we are in, as you can remember, we are kind of, at the 1 terabyte a day kind of territory. So this is definitely big data. Storage, we need two kinds of storage. One, what I call sort of forever storage, meaning it will store, this is the master data set. It will store the data forever, unmodified, right? And this will support actually batch queries or like aggregate queries. And I also need another storage for real time, meaning I want to look up things very quickly. I have like an iPhone app that shows my home temperature. So when I fire up the iPhone app, I want to see the latest temperature in like within a second, right? So this is a real-time query. And both of these things need to be scaled. So kind of a data, so looking at the data spectrum, we can sort of see, so starting with gigabytes here all the way to petabytes. And on the vertical axis, we have access time, so starting real time all the way to batch. So Hadoop, as we know, is kind of here, right? Basically, Hadoop is proven at petabyte scale, but queries on Hadoop are batch because most of the queries are built on MapReduce framework for Hadoop, and MapReduce essentially is a batch system. So what we need is something around here that kind of scale to maybe like hundreds of terabyte scale and give us real-time queries. So for this, we are looking at NoSQL databases. So most popular ones are like Cassandra, HBase, Vertica, along those lines. So for our storage, I think it's pretty much Hadoop, right? Because HDFS has been proven at scale, scales very well, it's fault tolerant. It's been proven, right? So there are a lot of companies try to come up with the HDFS replacement. None of them kind of succeeded so far, at least as far as I can tell. Real-time storage, we are going to go with the NoSQL. Right, so again, HDFS very quickly. HDFS is a distributed file system, runs on multiple nodes, and what it does is it makes multiple copies of your files, right? So when you drop a file in HDFS, the file is automatically replicated. So basically, for example, even if I lose node 1, that's okay, right? Because I have copies of all the files on other nodes. So that's how HDFS actually guarantees your data survives hardware failure, and this scales to like petabytes in size. And kind of a cost for storage-wise, you can see, right? So this is kind of I took it from Hortonworks. So you can see this is like cost for terabyte storage. So your traditional SAN, NAS drives, they're pretty pricey, right? This is like around 40,000 onwards. Hadoop, you can see, it's around 1,000, 2,000 a terabyte. Only thing cheaper than Hadoop is probably cloud storage, like Amazon S3. The reason they're cheaper is they build at really massive scale, so they get cost savings. And most of the time, most of the cloud storage is just storage bits, right? They don't do any processing. Hadoop gives you storage and processing, right? So Hadoop gives you a pretty fairly reasonable rate for storing large data. So okay, so HDFS is our source, right? So we are, it's cheap enough, it's proven, and also another nice thing about HDFS is once I dump files into HDFS, they are not modifiable. I cannot go and update the files. So it's a pretty nice way to kind of if you want to ever go back and look at the logs from say 2 years ago, go back, go to HDFS and look at the logs, because we know the files cannot be modified. So this is what we call sort of the source of truth, right? I'll sort of skip this for now. I'll put the slides a little later. Choice for NoSQL. So we sort of figured out, okay, HDFS is our master storage. What about NoSQL? There are way too many. There's so popular ones are like HBase, Cassandra, and Accumulo. Accumulo is basically sort of an HBase cousin that came out of NSA, and in a strange twist of things, it's actually open source, and you can actually use it. In NoSQL, very quickly, CAP theorem basically says, there are 3 properties of partitioning: consistency and availability. You can have to pick your camp, right? You can have all 3. So basically, you're going to either, if you choose HBase, you're going to get great consistency, but your system may not be available all the time. If you choose something on this camp, say Cassandra, it has great availability, but it may not give you a consistent view of data all the time. Now, there's no right or wrong answer here. Depending on your application, which one do you read most, whether you need availability most or consistency most, you sort of pick and choose one of these. Right, right, so for our store, we figured it out. It's HDFS, and we'll go with the NoSQL, whether it's PHP or Cassandra or Accumulo, any of the NoSQL flavors that you guys are comfortable. All right, we're coming over to the next part, query. So now that we have our data coming in, data is processed, my data is pushed to all the storages, what kind of queries are we going to run on this? So I look at queries again in sort of two segments. One is a real-time query, right? For example, let's say I have like an iPhone app that's showing me my latest temperature. That's a real-time query, right? It's going to go to the system and fetch the latest temperature, milliseconds range. And also I have aggregate queries, right? This is where sort of a lot of the insights come from. We sort of say, what's the average thermostat setting in this zip code? Do people here like it cold? They kind of like set the thermostat a little higher. And all of these aggregates, they actually go through lots of data points. And these don't need to be real time, right? These are queries that can take minutes or hours. These are batch queries. We are okay with them. So for queries, remember we have two storage engines, one NoSQL for real time, and HDFS for sort of our master storage. So it's very easy. So our batch queries are going to go to Hadoop or HDFS because time is not an issue, or latency is not an issue. Our real-time queries are going to go to a NoSQL store where you can fetch data in milliseconds in real time. Right? So we sort of figured this out too, right? So for batch queries, we'll use Hadoop, either MapReduce or Spark MapReduce. For real time, we'll query the NoSQLs directly. So this is the final, kind of the final architecture. We sort of going through all the components. So a capture is done by Kafka. Events come in here, and events are then pulled by Spark streaming to process in sort of near real time. And then the events are actually saved to an HDFS for long-term storage, and also pushed to say a NoSQL that maybe that only may keep like recent data, like let's say last 1 month, last 3 months of data. And our query is basically we query both storage systems. So batch queries go here, NoSQLs go, real-time queries go there. So in essentially, sort of what we have sort of done is kind of come up with some sort of a Lambda architecture. So again, Lambda architecture came out of Twitter about basically how to do big data processing in real time and also in batch. So if you look at this, the new data that comes in, that gets sent to both layers, right? It's, my new data also gets sent to my real-time storage, and also it's sent to my master data set. It could be a Hadoop HDFS. And the reason we are doing this is real-time queries come here. For example, what's the latest temperature? I just come right here because I don't care about historical data, right? I just want the latest data, and I come to the real-time view. And even the master data set is sort of a source of truth, right? This is where it keeps all the data. So if you want to go back and look at data from 2 years back, we can. And this powers batch views. For example, it could be something like our analytics queries. What's the average temperature for a zip code? What's the pretty much anything you want to do aggregate over a large amount of data, you will do by this layer. And some other queries, you can see this query, for example, is going to here real time and also batch. Because for some queries, you need to basically query both layers and aggregate the results. And that's okay, right? Because these queries are usually, because you want to have look at some real-time data and also some sort of archival data. So that's what basically Lambda architecture means. And again, this sort of came out of Twitter from their kind of experience of handling data at large scale. So if we were to sort of convert our architecture to Lambda, this is what we have. Our data comes to Kafka, right? So Kafka makes sure data is captured and no events are lost. Right? That's what we want. We don't want to lose any events. Then the data is pulled down into Spark out of Kafka, and Spark, you can say, as it processes events, it's pushing events to either HDFS and NoSQL. So in NoSQL, you could set up a policy like, my NoSQL stores only, say, latest data, last 3 months worth of data, last 6 months worth of data, whatever our policy is. And you can see queries. Our batch queries are going here. Our real-time queries are going here. So basically, this is our Lambda architecture. So the architecture at this point is scalable, meaning each component, like Kafka scales independently, Spark scales independently, HDFS. So every component here can scale independently based on the load. And that's very critical because sometimes You may want to have a large Kafka cluster, but like I say, a 30-node Kafka cluster. But your Spark cluster, you only like a 5-node Spark cluster, right? So it's very important for these components to independently scale up and down. And they are fault tolerant. Every component here is built for cluster-wide cluster compute. So they can survive hardware failures. There's built-in redundancy to make sure they survive hardware failure and the data is safe. Right? And the cool thing is they're all open source. So all of these pretty cool systems, pretty much they're all open source licenses, right? All right, so one thing we haven't talked about is security, right? Which we are going to hear a lot today in the conference is these IoT devices are great, but what about security? And in one of the surveys, security is sort of one of the top concerns of people in internal things. Like you ask people, okay, what do you think about internal things? What could be the issues? And people say, yeah, we don't know about what's happening to the data. We don't know how secure the data is, right? So security, that's a whole another talk in itself. But we know it's an important part of the infrastructure you need to take into account. So, right. So now that we have all the components figured out. We've got Kafka, we've got Cassandra, Hadoop, right? Spark. So this should be easy enough to build, right? We kind of figured out all the components. So the joke I tell is, just because I learned to fly doesn't mean doesn't mean I can fly a 747, right? So another joke I tell is like at scale, nothing works as advertised. So I always tell, there's a PowerPoint version, which you guys are seeing here, and there's a reality, right? Which there's a huge gap in between. So if you're going to build this, and we talked to a lot of clients who are trying to build this. So we said, hey, why don't we build the base infrastructure as open source, right? Because everybody's trying to build the same infrastructure over and over again. They have Kafka streaming, Cassandra, and then Hadoop. The same layers are being pretty much built by every single one. So what we are trying to do is, at Elephant Scale, we are trying to build this base platform as open source. All right, so the reason we are doing it open source is we are big believers in open source, and I believe the base infrastructure needs to be open source so it can get pretty good adoption. You can add value-add services on top of it and do like a premium premium things later on, but the base infrastructure has to be open source.